Thank you so much, Giovanni, for organizing this wonderful seminar series and also for having me here today. So today I will discuss 3D nanomagnetism in interconnected nanowire networks. In fact, there has been a lot of interest in nanowire networks or other types of low density materials such as foams in recent past, because they are very fascinating materials. They have very high surface areas, very high porosity, lightweight, and the nanoscale dimensions. So there are many very interesting potential applications spanning from biomedicine to photovoltaics, thermoelectrics. We actually got started working on such nanowire networks around 2010 or so, trying to develop very interesting types of high energy density laser targets. Such lightweight and low density material also have applications in catalysts and energy storage. And the magnetic side of this have really seen explosive growth over the recent years. And I thank Amalio for a great introduction. In fact, around, I think 2016 or so, Peter Fisher organized a workshop at Advanced Light Source, and Amalio, Claire, Donnelly, and others came, and we discussed the many exciting opportunities, and many of them have materialized over the last several years. For example, so I'll just be very quick, such 3D magnetic systems offer exciting opportunities to explore their structure, topology, and frustration, as highlighted by this recent review articles, and also the 3D storage racetrack memory from Stuart Parkin and colleagues. And also such networks, because of their high connectivity and complexity, they offer opportunities for neuromorphic networks, for example, using resistive switching. The curvature in such 3D systems also offer opportunities, including curvature-induced Jarzynski-Maria interaction, exciting types of chiral spin textures, such as Hofmann, Mobius band. And also there have been a lot of interest in artificial spin ice, where the dipolar interaction and also the geometry of such networks leads to frustration and leading to many magnetic states. And there have been proposals of using them for complex computation. And the networks also can be used to modify the electric and the thermal transport properties, leading to interesting results in spin caloritronics. As Amalio has already mentioned, there have been very big challenges, both in terms of synthesizing such 3D structures and also characterizing them. So here are some interesting studies looking at, for example, using electron holography to study nanoscale magnetic spirals, and also X-ray tomography has been used beautifully to show, for example, the differences in 2D versus rolled up thin films, and then Claire and Amalio's work on this nanoscale 3D pillars and this double helices. But in general, it's very difficult both to make them and to study them. So we were interested in using some easily accessible techniques and tools to fabricate and understand them. So in my talk, I will primarily talk about nanowire networks with potential applications in 3D information storage. And if I have time towards the end, I will illustrate an unusual use of such nanowire networks for filtration. So the way we make our samples was through nuclear track etching, and we expose some radioactive source in front of some templates such as polycarbonate, where the decay fragments, alpha particles, will go through the membrane, create damaged tracks. Then we can etch them out to whatever size we desire. And as illustrated in this earlier studies. And so we can fill up the pores by electrochemical deposition to form nanowires. So in this study, we did more than just the normal single angle nuclear track etching. And so in addition to this, we did multiple additional tracking at a 45-degree co-latitude angle at a symmetric azimuthal angles. So for example, this could be 5 or 3 angle tracked. And afterwards, we etch out the tracks and we electrodeposit materials and fill up the pores. And then at the end, we have this freestanding networks. And so here is an example of both 5 and 3 angle tracked networks. And on the top one, we show networks that are tracked at 5 angles. And you can see an example of the intersections. At the bottom, we have examples of a 3 angle tracked. And so in either case, we can achieve with a single sheet of such networks, the density is on the order of 100, 125 milligram per cubic centimeter. And we can actually roll up such sheets of networks into a small volume, and where the density is further reduced to 40 milligram per cc. And the porosity is very high, above 99%. And so in the following, I will be talking about magnetic cobalt networks prepared in this fashion. And I will focus on 3 angle tracked. So in addition to 1 normal incidence, we have 2 other tracking at 0 and 180 degree azimuthal angle. So basically we have a single irradiation plane, which are highlighted by this white dashed lines. And so this is a cross section of the irradiation plane. And we have estimated the number of intersections. So by considering the various geometries we have in the sample, the 2 adjacent nanowires, they are either parallel or 1 normal incidence, 1 at 45 degree, or both of them at 45 degree. And we can estimate the overlapping areas. And from the fluence of the tracking, we can estimate the number of intersections. So I will be talking about cobalt networks prepared this way that have 75 nanometer diameter and on the order of 1 billion intersections per square centimeter. So in addition to the 3 angle tracked networks, we have also prepared same size single source, single irradiation parallel nanowire networks as a reference point. So we first look at their magnetic response using vibrating sample magnetometry, and this is a conventional behavior for the untracked, just single tracked parallel nanowires. We first vary the angle. So here we use theta to represent the angle where the magnetic field is within the plane. And this theta track the angle between the field and the polycarbonate membrane. So theta equals 0 is the field in the membrane plane and perpendicular to the nanowires. We see a typical hard axis loop. As we increase the angle, and then at a 90 degree, we see this easy axis behavior with the highest remnants. And now we go to the networks. So first, let me also introduce another angle phi. So this angle phi is the magnetic field makes with respect to the irradiation plane normal. So theta equals 0 means the field is perpendicular to that irradiation plane. Theta equals 90 degree means the field is within this irradiation plane. So first, let me put the field within that plane and just vary this theta. So this is comparable to the previous parallel nanowire case. And at 0 degree and 45, and we see how they change. Of course, the number of nanowires that are aligned with the field vary. For example, at this 45 degree geometry, only 1/3 of the wires are parallel to the field. Keep in mind that we are using the same fluence for each tracking angle. So 1/3 is parallel to the field, 1/3 is perpendicular, another 1/3 is at a 45 degree. And then finally, at a 90 degree, we have 1/3 parallel to the field. 2/3 are at 45 degree. And this corresponds to the highest remnants because we have the largest proportion of the nanowires that are the projection are aligned the magnetic field direction. And now if we look at the other geometry where we vary this phi angle. So here we are, when the phi is 0 degree means the field is perpendicular to all the wires. Again, we have this hard axis behavior. And finally, at 90 degree, we have the highest remnants. Qualitatively, this series look kind of similar to the parallel nanowires. 0 degree means the hard axis, 90 degree is the easy axis, and in between it evolves. However, there's important differences. For example, the coercivity is very different. In the parallel case, it's 270. In the intersecting network, the coercivity at 0 degree is 570. It's much larger. So this indicates the network structure definitely played a role in the magnetic properties. Both there are magnetic coupling between adjacent segments, and also the intersections pings the domain warp movement and leads to the coercivity enhancement. So a simple question is whether our intersecting network is just a simple superposition of the parallel nanowires in this 3 different geometry. And we can just do a comparison. And here the red curve shows the superposition of these 3 different geometries comparing to the intersecting network. And obviously they don't agree. So this again shows the network geometry made a difference in this somewhat different magnetic behavior we saw in the networks. So to further get to the details of the magnetization reversal, we did a first order reversal curve study, which essentially allow us to get the magnetic signatures or fingerprints of such networks. We compare parallel nanowires and also this intersecting networks in different geometries. But before I dive in to explain this sets of complicated patterns, let me just quickly go over the basics of this technique. And this FORC method measures the magnetization in the following way. So instead of a conventional single major hysteresis loop, we first saturate the sample and then bring the sample to a particular reversal field HR. Then we start measuring back up to saturation. So the magnetization, any point on this FORC is a function of both the reversal field and applied field. And we repeat this to more and more negative reversal field. So we measure a family of such FORCs. And afterwards, we do the second order derivative of magnetization with respect to the reversal field and applied field. So this, in essence, allows us to measure the distribution of elemental hysteresis we call hysterons, which have unit magnetization. And therefore, you just need a switch down field and a switch up field to characterize. So what we are doing is, for example, by bringing a sample to a reversal field, we are switching down a set of the hysterons that have switched down field in this range, shown in red. And then by measuring back up to this reversal field H, applied field H, we are switching back up a subset of the previous hysterons that have switched up field in this range. Okay, so we're disturbing the system to see how they respond. And the FORC distribution, we can show them in this 2D plot or 3D, but let me show a few representative ones. If the constituents are all identical, let's say I have identical nanoparticles, there's no interaction and there's no coercivity distribution, I will just get a delta function. If I do have a coercivity distribution, but there's no interaction, then I will see this horizontal ridge in this coercivity and the bias field coordinates. I should mention this coercivity distribution that measures the half width of the loop, and this bias measures the shift of the center of the hysteron from the origin. And when we have interaction, but no coercivity distribution, we have a vertical ridge that indicates the interaction. When we have both coercivity distribution and interaction, we see something that looks like a wishbone structure. And in reality, we see all these types of distributions in actual experimental systems. For example, in this iron fluoride thin film system, we see this delta function. In non-interacting nano dot collections, we see this horizontal ridge. And in this nickel nanowire array, we see this vertical ridge. And you can imagine that adjacent nanowires, they would prefer to be antiferromagnetically coupled. So this demagnetizing dipolar interaction leads to a sharing of the family of FORCs. You can imagine each hysteron has a square box, a boxy, this hysteresis loop, and you are stacking a whole bunch of them on top of another, and this demagnetizing dipolar interaction will shear them. And so this, you can see these curves, they all initially go out horizontally, then go up, and then they show up in this FORC distribution as this vertical ridge. And there's also a little tail because of the coercivity distribution. And then this case, when we have interacting elliptical cobalt nanodots, depending on whether it's the magnetizing or demagnetizing dipolar, we can see different signatures. So coming back to our networks, we first look at parallel cobalt nanowires. And so here are the 3 FORCs shown in 2D and 3D. And for example, at this geometry, when the field is parallel to the nanowires, we see 2 vertical ridge. And this feature corresponds to that demagnetizing dipolar interaction that I just showed. And then there's a second ridge, which shows up more clearly when the field is perpendicular to the nanowire. And this is from just the reversible component. And this, in fact, is the subject of one of our recent papers to purposely look at reversible switching, try to distinguish that from features that are close to zero coercivity, soft magnetic components. And from there, we can actually extract phase-resolved magnetic hysteresis loops. Now, going on to the interconnected cobalt nanowire networks, in this case, when the field is perpendicular to the membrane, again, we see this qualitatively the similar 2 vertical feature, except that this one now is a little bit more like a wishbone structure. So it has both this vertical ridge and also a horizontal finite distribution. So in this case, the extent of this vertical ridge is an indication of the dipolar interaction. And the extent is somewhat smaller than the previous case. Here it's around 800 Oersted, somewhat smaller than the previous parallel nanowire case of around 1100 Oersted. That shows the dipolar interaction is reduced and because of the intersections. And in this geometry, when the field is at 45 degrees to the membrane, we see this feature further gets suppressed. So the dipolar interaction is further suppressed. You can see it from the vertical direction. And the horizontal spread actually is an indication of both the intrinsic coercivity distribution and the dipolar interaction. So here we see the effect of intersection-mediated domain propagation. Then finally, when the field is in the plane of the membrane, in this geometry, we see this FORC feature collapses to a symmetric dome. Okay, this corresponds to essentially no dipole interaction. And here we are just seeing the intrinsic coercivity distribution. By the way, this kind of a wishbone structure is also observed in other studies, such as some early generation of magnetic recording media. Again, this is a manifestation of both the interactions within the material system and the finite coercivity distribution. And the details of the extent of such distributions are described in a separate publication earlier. And then finally, when we vary the irradiation plane with respect to the field, we see this trend. Again, these two are similar to the previous geometry. And then in the final, in this geometry, when the field is perpendicular to all the wires, we again recover this single reversible vertical ridge. So to recap this series of forks, what we see is initially when the field is parallel to all the wires, we see demagnetizing dipolar interaction dominates. When the field is perpendicular to all the wires, the shape anisotropy dominates. And in between, we see signatures from the intersection-mediated domain propagation and motion. So this offers an interesting possibility that by controlling the applied magnetic field geometry and the strengths, we can selectively address a certain set of the nanowires. For example, in this case, if initially we apply the field perpendicular to the membrane, the field is just enough to saturate the nanowires that are parallel to the field. And then by rotating to this geometry, we can force the magnetized region to propagate. And so in principle, we can encode the magnetic information into the magnetic state of such network and let it propagate. And recently, we have also measured the magnetoresistance signatures of such network. We see clear signatures of intersection pinning of the domain walls. And they also offer an opportunity to explore multi-state memristors because of the pinning of domain walls. Incidentally, we have actually made a collection of various FORC capabilities, and we made a little FORC library, and this can be accessed on my website or through this QR code. I want to also mention briefly the potential use of such 3D networks for information storage in regard to this 3D racetrack memory, for example, which is a fascinating idea, but on the other hand is also very complex. So one possibility to address the numerous domain walls or skyrmions possibly could be through chemisorption. We have recently shown that through chemisorption of oxygen or hydrogen onto ferromagnetic surface, we observed induced Jarzynski-Maria interaction. And this is because of the interfacial electric dipole moment through the charge transfer, and because of the difference in the electronegativity of oxygen versus the ferromagnet. And in this case, we were able to change the winding number of a skyrmion at room temperature through oxygen chemisorption. And on the right, we were able to switch the domain wall chirality through chemisorption of hydrogen. And then you can see, for example, in this case, the contrast change from black to white, corresponding to the chirality change of the domain wall. And also we have found that chemisorption hydrogen can also induce anisotropy change. And this allows us to write or delete magnetic skyrmions at room temperature just through hydrogen chemisorption or desorption without using any magnetic field or electric field or electric current. So we are essentially pulling magnetic skyrmions out of thin air. And this potentially could be used to address 2D or 3D racetrack memory, where through chemisorption, we can reverse the domain wall chirality, for example, which in turn can lead to opposite propagation directions. And such an effect can also be integrated into solid state magneto-ionic devices. In the last maybe 1 or 2 minutes, I'll just quickly flash out one interesting, unusual use of such nanowire network, that is for filtration. We know the COVID-19 has caused so much disruption globally, but even before that, air pollution has been a big challenge. And most of the pollutant particles are below 0.3 micron. They are so-called long-penetrating particles, and they pose the most health risk. And it's challenging to filter such small particles because conventional mechanisms are least efficient at this size range. And the N95 mask, for example, they rely on electrostatics, so it cannot be easily cleaned and reused. So we used actually metallic nanowire networks. I'll skip some of the details. Similar to the way we construct the nano network, we can construct a 3D foam. And here, SEM picture shows the microstructure of such foams, which are tunable, and we can use them. They are very lightweight and robust. So the same lightweight foam can support a big load. And we use them as a filter. They have a very good breathability. So in a nutshell, they are comparable to N95 mask, or even in some cases twice as good. The efficiency is excellent. We show above 95% filtration efficiency, particularly for this 0.1 to 1.6 micron particulate size range. And this is especially relevant for COVID-19. And such a foam can be reused and recycled. We can easily rinse and then clean up the foam and reuse. We actually entered into a BARDA Mask Innovation Challenge in the US, and we were selected as one of the 10 winners last year. Okay, so let me summarize. I've shown examples of interconnected nanowire networks, which could be an interesting platform for 3D information storage, and also there's potential for neuromorphic computing. And this last example shows some interesting applications in filtration. I'd like to thank funding support from NSF, DOE, SMART, and UC Davis and Georgetown. And finally, the people who actually did the work, starting from my group still at UC Davis, Nat Burks, Dustin Gilbert, Peyton Mary, Chad Flores, to folks at Georgetown, James Malloy, Alberto Quintana, Chris Jensen, and my colleague Gen Yang. And we also collaborate with Tom Felter and Sandia, Sup, Chavanichko Borikan, and Sergei Kuchiev and Jeff Koving at Livermore National Lab. With that, I'll stop here. Thank you very much for your attention. I'll be happy to answer questions.